Okay, so today we continue with chapter 5. We'll cover probably 5.3 and 5.4 today. And 5.3, this section is called the Algebra of Sets. And what your book means by this is what properties the basic set operations have, right? So we learned about intersection, union, set theoretic difference, and complement. But of course, taking these operations have certain properties. So let's warm up by proving a property that we already know, but I'll call it a theorem. So let A, B, and C be subsets of some universal set U. Then two things are true. One is that A intersect B is a subset of A, and A intersect B is a subset of B. So this just says that the intersection, if you intersect a set with another set, the result only could possibly get smaller. Sorry, this is not actually the second thing. Of course, it holds for B too, by symmetry. What I meant to say is that A is a subset of A union B. So also, if you union a set with another set, it can only get bigger. And then the second thing is, if A is a subset of B, then if you look at A intersect C versus B intersect C, basically if A is contained in B, then if you intersect with the same set, you get the same containment. And also, if you union with the same set, you get the same containment. Okay, so this would be a good opportunity to practice some of the set theoretic proof techniques that we discussed last time. So I will prove the first statement, and I'll leave the second statement as an exercise because the more practice problems you have, the better. Okay, so proof. We prove the first statement. Okay, so now suppose A and B are some subsets of universal set U. Just the setup. I want to prove that A intersect B is a subset of A, which means that I want to do an element chase. So first, we show A intersect B is a subset of A. How do you do this? Let X be an arbitrary element of A intersect B. Then by definition of the intersection, X is in A and X is in B. In particular, X is in A. So what have I shown? I've shown that if X is in A intersect B, then X is in A. Hence, A is a subset of A intersect B. Okay, so I only included this sentence, this in particular sentence, just to help my reader, right? Because my reader knows I'm doing an element chase. My reader knows what I need to prove is if X is in A intersect B, then X is in A. So it's nice to start with let X be in A intersect B and end with therefore X is in A. Right? That makes it just a clearer thing to read. Okay, now for the second statement. So let's say now we show that A is a subset of A union B. To that end, let's let X in A. Then certainly it's true that X is in A or X is in B because X is in A. So if you, right, so this X is in A or X is in B is definitely true if X is in A. Right, therefore, X is in A union B by the definition of the union. So we have shown that if X is in A, then A is in A union B. So we've shown that A is a subset of A union B. Okay, so nothing really tricky here, right? These are just two element chasing proofs, where basically all we've done is we've used the definition of the intersection, the definition of the union, and the definition of subset, basically. And so the second proof will be similar, right? You should write it up carefully, but for example, if you want to prove this, the first part of the second statement, you suppose that X is in A intersect B. That means that it's in A and it's in C. But since A is a subset of B, if X is in A, then X is in B, which means that it's in B and it's in C, which means that it's in the intersection. Okay, so the only way to get practice is just try to write it up as cleanly and nicely as possible. Okay, so your book, so these are two nice properties that union and intersection have. Again, if you take a set and you intersect it, it only gets smaller, possibly. If you take a set and you union it, it only possibly gets bigger. And if one set is contained in another, then if you intersect them both with the same set, or if you union them both with the same set, you get the same containment. These are nice properties of union and intersection. Your book gives two big theorems with several of the properties of set operations. So just for your notes, that way you can have like a number to reference this big theorem. Let's list them all out and call this theorem just the algebra of set operations. This way we can always go back to this list if we're ever not sure if we're allowed to do something with a set. Okay, so I'm going to list a bunch of properties, but I won't prove them all. I'll leave them to you to prove. So this is what it says. Let A, B, C be subsets of a universal set. Then the following properties hold. So there's 11 of them. So let's just talk through them. One, if you intersect A with the empty set, or you union A with the empty set, what should you get? Hopefully you can fill this in without me telling you. If you intersect with the empty set, you get the empty set. If you union with the empty set, you just get back the set you started with. Two, if you intersect with the universal set, or if you union with the universal set, what happens? Again, hopefully I don't need to tell you that if you intersect with the universal set, you just get back the set you started with. If you union with the universal set, you get back the whole universal set. Okay, 3, this is called the idempotent laws. Okay, so what does idempotent mean? I think maybe this is actually Latin, right, rather than Greek. Idem means like same, like identical, idem. And potent means power, like potential or omnipotent. So idempotent means same power. That doesn't make it that much clearer, though. What the idempotence laws say is that if you intersect A with itself, or you union A with itself, you get back A. So it's like that always explains the same part, right? If you do an operation of something with itself, it stays the same. Idempotent laws. Okay, 4, commutative laws. Hopefully you can guess what this means. This says that set intersection and set union are commutative operations, right? And if you take A intersect B, it's the same thing as B intersect A. If you take A union B, it's the same thing as B union A. Okay, 5, the associative laws. This says that intersection and union are both associative set operations. So it doesn't matter if you're only doing intersections or if you're only doing unions, the order in which you perform them doesn't matter. Okay, if you mix intersections and unions, though, the order will matter. We'll see that in a second. Okay. By the way, all of these things are not things that we're assuming about sets. All these things you can prove about sets using just the definitions of the set operations and basic logic. Okay, so whereas for the real numbers, we assume they were commutative, for sets, it's a theorem that taking these two set operations is a commutative operation and associative. Okay, the distributive laws tell you how intersection and union behave with respect to one another. So what does the distributive law say? It says that if you intersect A with B union C, it's like you can distribute the intersection over the union. So if you imagine intersection as like times and union as plus, this says that a times b plus c equals a times b plus a times c. So it's like the normal distributive kind of thing. And also, if you union a with b intersect c, you get a similar sort of distributivity. Okay, 7 is about taking, well, two things. One is about taking double complements. So if you take the complement of A and then you take the complement again, you get back A. And the second is if you take the set theoretic difference of A and B, it's the same thing as intersecting A with the complement of B. That's because both of those things mean all the elements that are in A, but not in B. Okay, 8 tells you what happens if you take the set theoretic difference with the empty set or the universal set. Hopefully you can guess that this is A and this is the empty set, right? It's either you take nothing away from A or you take everything away from A. Okay, 9 tells you about the complements of the universal set and the empty set. So the complement of the empty set, that's everything, and the complement of everything is nothing, is the empty set. 10, these are De Morgan's laws. Think back to what De Morgan's laws told you. De Morgan's law told you how to like not an and statement or how to not an or statement. So in terms of sets, and is kind of like intersection and not is kind of like complement. So this is called De Morgan's laws because it's kind of like knotting an and statement. Okay. Maybe I'll just put in blue what the old De Morgan's laws were. I mean, the De Morgan's laws for logical operations was this and this, right? For sets, if you take the complement of A and B, sorry, the complement of A intersect B, it's the complement of A union the complement of B. And if you take the complement of A union B, it's the complement of A intersect the complement of B. So hopefully you can see why those are called De Morgan's laws. And then lastly, the 11th law is that A is a subset of B if and only if B complement is a subset of A complement. Okay, so like I said, these are all theorems. They're not axioms. I'm not assuming that set intersection is commutative. The fact that set intersection is commutative just follows from essentially the truth table of and statements. So I encourage you to prove these things. So if you are going to ask me, for example, for some more practice problems, I will say, go back and prove, I mean, practice problems in chapter 5, I'll say, go and prove everything in the algebra set operations theorem and then come talk to me again. Okay, that's it. I will prove one thing because it illustrates a standard technique. So let's give one more theorem. Let A and B be subsets of some universal set U. Then the following are equivalent. Okay, often abbreviated TFAE. So if you're in a math class and someone says TFAE or writes TFAE on the board, they mean the following are equivalent. And then they're going to list some things. So we're going to list 3 things. A is a subset of B. A intersect B complement is the empty set. A complement union B is the universal set. Okay, now if someone says a bunch of statements are equivalent, what they mean is that they are logically equivalent. What does logically equivalent mean? It means that if one of them is true, then they're all true. If one of them is false, then they're all false. Right? Logically equivalent means they take on the exact same truth values. So if someone says something statements are equivalent, it means, right, if we call like this one P and this one Q and this one R, they mean P if and only if Q, P if and only if R, Q if and only if R. That's what they mean by equivalent. All of these statements imply one another. Okay, and the standard technique that you use to prove something like this is, okay, so to prove that a sequence of statements are equivalent to each other, prove a sequence of conditionals so that there is an unbroken chain of conditionals from each statement to every other statement. Okay, what do I mean by this? If we are trying to prove 1, 2, or P, Q, and R are all equivalent, then actually let's even go to a bigger example. Right? Suppose we have 4 statements, P, Q, R, S. So to show that these are all equivalent, then in principle, a priori, you would need to prove 6 separate if and only if statements, right? Technically, you would need to prove P if and only if Q, P if and only if R, P if and only if S, Q if and only if R, Q if and only if S, R if and only if S. That would show that every statement is logically equivalent to every other statement. But what this technique says is we don't need to do this much work. We just need to prove enough conditionals such that you can get an unbroken chain from every statement to every other statement. So this technique says it is enough to show, for example, one choice is P implies Q, Q implies R, R implies S, and S implies P. If you can prove these 4 conditionals, then there's an unbroken chain from any statement to any other statement, right? If you want to get from Q to P, you can go Q implies R, R implies S, S implies P. And since P implies Q, that shows that P implies Q and Q implies P. If you want to get from Q to S, right, you go Q, R, R, S, S, just Q, R, R, S rather. So if you've proven these 4 things, then that's enough to show that they're all equivalent to one another. Of course, this is not the only unbroken chain that you could prove, right? It's also enough to show, let's say, P implies Q, Q implies R, R implies P, and also something like S if and only if Q. Right? Why? If you prove the first 3, that's like proving that all 3 of P, Q, and R are equivalent to one another. So you can get between P, Q, and R. And then this one proves that you can get from S to Q and from Q to S. So now if you want to prove that P implies S, you go P to Q and then Q to S. If you want to imply S implies P, you go S to Q, Q to R, R to P. Okay, and the point is that if you have an if and only if statement, some of the implications will just be easier to prove than the others. So what this technique gives you is some flexibility in how to prove the following are equivalent statements. Of course, you're always going to have to do some amount of work, but sometimes some of them are easier to show from the other ones. So if you remember back to 308 linear algebra, whenever you took it, you had something called like the big theorem or the unifying theorem or the invertible matrix theorem, which was like a bunch of equivalent statements on a matrix being invertible, right? It's like the rows were linearly independent, the columns were linearly independent, the rows spanned, the columns spanned, right? Every ax equals b had a solution, whatnot. There were like 14 statements or whatever in that theorem in 308. And the point was that some of them were very easy to prove implied other ones of them. And every time you added something to the theorem, basically you only need to prove that it was equivalent to any of the ones that you had already proven were equivalent. So, right, if you have a list of like 10 things and you want to add an 11th thing, you don't want to have to check that it's equivalent to all 10 things. If you know that the 10 things are equivalent, then you only show that it's equivalent to one of them. Or even that it's implied by one of them and it implies another one of them, right? What I'm trying to say is here you had 10 things here, right? P1 up through P10, and then you want to add an 11th thing, P11. You didn't need to show that it's equivalent to every one of them. If you know that these are equivalent, you can just show like, oh, P3 implies P11 and P11 implies P6. And now you've added P11 to the unbroken chain. So it's a really nice technique in that it gives you a lot of flexibility. Okay, but let's prove this. So that's enough blabbering from me about this technique. Let's just put this on the next page so then we can look at it while we're proving it. This is by far the fanciest thing I can do. Okay, in fact, let's even move this over here to give us a little bit more room. Okay, so if you're going to prove a bunch of statements are equivalent, though, as always, you need to give your reader some help so that they don't get confused. Okay, so what I'll say is, what I'll prove, so we will prove that 1 implies 2 implies 3 implies 1. Okay, and I'll say that even in your formal proofs, I will allow you to use these symbols. You could also replace all of these words by these arrows by implies. That's okay. But so I'm telling my reader what I'm going to prove, and then if they're looking at this like, oh yeah, well then that would prove that they're all equivalent because you have a chain from any one to any other one. Now I'll give my reader like, again, some signposts. So here I'll say, okay, this is just notation. This is just like saying chapter 1. What I'm saying is this part will be 1 implies 2. The nice thing is that I actually believe that we proved this one last lecture. So let's take a look. Did we prove A is the subset of B implies that A intersect B complement equals the empty set? Yes, this is the last thing we proved last time. If A is a subset of B, then A intersect B complement is the empty set. So 1, we proved this at the end of last lecture. Okay, now 2 implies 3. Let's suppose that A intersect B complement equals the empty set. Now, I'm trying to understand A complement union B. Okay, but as I'm looking at this, one thing I'll notice is that the difference between 2 and 3, the difference between this and this seems to be like I put a complement on A and I took off a complement on B, and then I switched the intersect sign with a union sign, which to me suggests that maybe De Morgan's laws will be helpful here. Okay, so in other words, maybe I should complement the whole thing. Well, we know by the algebra set operations that the complement of the empty set is the universal set. Hence, if you take the complement of the left-hand side, it's the complement of the right-hand side, which is the universal set. Now I can use De Morgan's laws. So now by De Morgan's law, or one of De Morgan's laws, we have A complement union B complement complement equals the universal set. All I've done is I've just De Morganed the left-hand side. And finally, by another property of sets from that algebra of set operations, B complement complement equals B. So A complement union B equals the universal set, which was what we wanted. Right, so 2 and 3 are equivalent basically just by De Morganing. Or 2 implies 3 just by De Morganing. I guess I could also prove 3 implies 2. But if I prove 3 implies 2, that's still not enough to prove that all of these 3 are equivalent because I can never get to 1. So the nicest thing to do here would be to prove that 3 implies 1. So suppose that A complement union B is the universal set. So we must show that A is a subset of B. Okay. So suppose X is in A. I want to show that X is in B. Well, if X is in A, then X is not in A complement. Then X is not in A complement. That's by the definition of the complement. Okay, but certainly X is in the universal set, which is equal to A complement union B. So if X is in this set, but it's not in A complement, it must be that X is in B, right? And hence, A is a subset of B, just like we wanted. Okay. So this is a nice thing to know, and just a good illustration of a very standard proof technique. Okay. So in the last bit of class today, I want to move on to section 5.4, because honestly, section 5.3, there's nothing really new here. It's just proving properties of set operations using proof techniques we already know. So I should leave it to you. Let me give you a new definition in the section called Cartesian Products, which is 5.4. Here's the definition. So let A and B be sets, or if you prefer, subsets of some universal set. An ordered pair is a single pair of objects A, B with A in A and B in B. Okay, so by ordered pair, we mean where order matters. In other words, the element from A has to come first, the element from B has to come second. Okay, to say that two ordered pairs are equal, this is if and only if A equals C and B equals D. Okay, so in the ordered pair AB, A is sometimes called the first coordinate of the ordered pair, and B is called the second coordinate of the ordered pair. Okay, so really an ordered pair is just a pair that's ordered. One thing from the first set, one thing from the second set. And you could tell if two ordered pairs are equal just by comparing if they're equal in every single slot. Okay, this lets me make the following definition. So if A and B are sets, then the Cartesian product denoted A cross B, or A times B, is the set of all possible ordered pairs xy where x is in A and y is in B. Another way to say this is that A cross B is the set of all ordered pairs xy such that x is in A and y is in B. Okay, and like I've sort of already said, generally this is read as A cross B. And also notationally, in this class, I'm not saying that it's standard, but we'll let A squared, if A is a set, this will denote A cross A. Okay, so the Cartesian product of two sets is a new set consisting of ordered pairs, in particular, every possible ordered pair. So before I give you an example, let me just say, to get this symbol in LaTeX, use \times. And then last commentary, Cartesian, this is of course named after famous French philosopher René Descartes, because maybe you've seen Cartesian product, or maybe you called the xy plane the Cartesian plane, also named after René Descartes, who invented it. The point is that this plane shows all possible ordered pairs of real numbers, right? This you can think of as R cross R, or if you take some real number, I mean, if you take a pair of real numbers like pi comma 0, that lives here, right? But this plane shows all possible, this is one way to visualize all possible pairs of real number. So it really is the Cartesian product of the two sets R and R. So I guess this is your first example, but let's take a very small basic example where we can enumerate everything. Maybe let's this A be the set 1, 2, 3, and B be the set AB. Then what is this set, A cross B? A cross B is the set of all possible ordered pairs, something from A, something from B. So how many elements are in it? There are 6. You have 3 possible choices for the first coordinate and 2 possible choices for the second coordinate, and they're all present in the Cartesian product. So this contains 1 comma A, 1 comma B, 2 comma A, 2 comma B, 3 comma A, 3 comma B. The elements of the set are ordered pairs. Okay, they're ordered. So like A comma 1 is not in A cross B. A comma 1 is in B cross A if you were to change the order of this Cartesian product. Okay, and again, the tricky thing, I think, for students, like if there is something tricky about this, is that the elements of the set, you think of this set as a set, each element is a pair. So you should think of the ordered pair not as 2 elements, but as a single object in the Cartesian product. Okay, so I say this can sometimes be confusing for some students. You'll see what I mean as you do problems on the Cartesian product, which I'll give you some. Whoops, what am I trying? I'm trying to, oh my gosh. I'm trying to add a page. So let's prove a theorem on the Cartesian product. For all sets A, B, and C, if you take A union B cross C, this is A cross C union B cross C. Okay, so this is a proof where, or it's a theorem that says that two sets are equal. So a good technique here would be to prove both inclusions by element chasing twice. And as we do the element chases, I'll show you sort of how to work with Cartesian products. Okay. So proof, we will prove both inclusions by element chasing. Okay, so let's prove that the left-hand side is a subset of the right-hand side. So suppose I want to take an element of the left-hand side. Right? I want to say, suppose that something is in A union B cross C. But the thing to remember is that the Cartesian product consists of ordered pairs. So an element in A union B cross C, it looks like an ordered pair. So when I take an arbitrary element, I'll take x comma y in this Cartesian product. Because I'm going to need to know about the individual coordinates of my ordered pair in my proof. Okay, so what does it mean to say that x comma y is in this Cartesian product? By definition, this means that x is an element of the first set and y is an element of the second set. Okay, so since x is in A union B, x is in A or x is in B. Okay, so there are two cases. Okay, why? What I want to show is that I want to show that this ordered pair is in this set. But this set is a union. So in other words, I just need to show that that ordered pair is in this set or it's in this set. But that will depend on whether x is in A or if x is in B. So there are two cases. Okay, now let me tell you a little trick about casework. I probably actually don't need that in this room, but for casework, you should always make sure that it's very obvious that your cases cover every possible situation. So I would say that your first gut instinct would be to let the cases be x is in A and x is in B. It's also my first gut reaction. But I think there's a better choice of cases here. Because if you were coming at this proof blind and you went and you looked at it and you said, okay, case one, x in A, case two, x in B, your next question would be, why is that all the cases? Right? The reason it's all the cases is because x is in A union B, but you don't know that if you just come in this proof blind. So in my opinion, stylistically, a better choice of cases is this. If x is in A, if x is not in A. Because now if I'm zoomed out and I'm just looking at this proof, I see the two cases. Oh, x is in A, x is not in A. That definitely covers every possibility. And in case two, if x is not in A, then since x is in the union, therefore x is in B. So if you're ever in a situation like this where x is in A union B and you want to break into two cases, you should make your cases x is in A, x is not in A, and then use the fact that x is not in A to conclude that x is in B. Okay? Okay, well, if x is in A, then since we know that y is in C, therefore x comma y is in A cross C. that's the definition of A cross C, is all ordered pairs where the first thing is in A and the second thing is in C. So x comma y certainly satisfy that. Hence, x comma y is definitely in the union of A cross C with something else. This is by the first theorem today. Right? A cross C is a subset of A cross C union any other set. Okay. Case 2, if x is not in A, then since x is in the union of A and B, it's definitely in B. And in this case, since y is also in C, we have that x comma y is in B cross C. So x comma y is definitely in B cross C union something else. In either case, we took the element x cross y that was in A union B cross C, and we found it, no matter what the case was, in the right-hand side set. So we have shown A union B cross C is a subset of A cross C union B cross C. Opposite inclusion. Suppose that I have an element of the right-hand side. Again, now the element of the right-hand side is a union. So it's two sets put together, but each of those individual sets is a Cartesian product. So an arbitrary element of the union will still look like an ordered pair. So suppose that x comma y is in the right-hand side. Okay, then x comma y is in A cross C, or x comma y is in B cross C. Again, there are two cases. Okay, case 1. X is in A cross C. Sorry, x comma y is in A cross C. I'm trying to prove that x comma y is in A union B cross C, right? But by definition, let's say if this, then x is in A and y is in C. So x is certainly in A union B, which means that x comma y is in A union B cross C. Okay, case 2. If x comma y is not in A cross C, then x comma y is in B cross C, because x comma y was in the union of those two sets. Hence, x is in B and y is in C. So x is also in A union B, and therefore x comma y is in A union B cross C. So no matter what the case was, we saw that this ordered pair is in A union B cross C. So we have shown that A cross C union B cross C is a subset of A union B cross C. Okay, and now we have shown both inclusions. So we conclude that the sets are equal. Okay, so I've tried to give my reader every possible hope of understanding the proof by trying to be as clear as possible. Okay, so like I said, you will have problems featuring Cartesian products. The thing to always keep in mind is that the elements of the Cartesian product, you need to think of it as a set full of ordered pairs. So a single element of the Cartesian product is an ordered pair. And we'll see that, I mean, these kinds of things pop up all the time, Cartesian products, as evidence of that. the Cartesian plane, R2 that you're used to, really can just be viewed as a Cartesian product of sets. All right, next lecture that we have, we will move on to section 5.5, and then maybe even start chapter 6. I'm not sure, depending on time.